into gasoline to raise the octane, but you cannot put too much benzene. All right. Now the next next process is excuse me, alkylation. Now alkylation is it's a chemical reaction process. You basically take olefins, C3, C4, C5, and isobutane, and then you combine them together. You can see you've got a C3, a C4, C5, and a C4. If you combine them together, you can get something in the gasoline boiling range. And these are the basic alkylation reactions. Isobutylene, isobutane to isooctane. Sounds very simple, but again, it's a reaction. And a reaction has to be carefully controlled because you may want to combine a C3 and a C4, but if you overdo it, you'll end up with a C20 or a C25 because they just keep adding and adding. So you have to control the reaction conditions very carefully. But there are basically two processes. One uses sulfuric acid, the other uses HF, hydrofluoric acid. Now, the good news, alkylation, it's got no lead, has no aromatics, vapor pressure is okay, and the octane is reasonably good. It's not quite as high as aromatics, but it's pretty good. The bad news, unfortunately, you need a source of these olefins, so typically another cracking unit like an FCC will make lots of olefins, and the alkylate's more expensive because of the processing cost. You know, nothing is free. If you process, obviously, there's utility costs, capital costs. So alkylate's a prime blending component, but it costs money. All right. Now, so much for diesel, for gasoline. For diesel, the equivalent for an octane is a cetane. And again, California has regulations on cetanes and the requirements. Cetane is basically for compression ignition engines. So you compress the fuel and heat it up, and you don't have a spark, but you just ignite from compression. And there's a standard test, and the reference fuel is, believe it or not, normal cetane, which is C16H34. That's 100 for cetane number, and this one is 15. There's also what they call a cetane index, which is a prediction method from other properties. You take the other properties, calculate out the cetane index. All right, so basically, as far as background, that's the background on gasoline and diesel. So the real sort of meat of the topic here is on upgrading the resid. But obviously, we have to upgrade it to something that we can sell, something that has the right kind of properties. Now, the first process is vacuum distillation. So instead of just a regular atmospheric tower, you have a vacuum tower. Second one we're going to talk about is propane deasphalting, and next one is visbreaking, and then coking, and we have 3 different varieties of coking, and we're going to concentrate on delayed coking. And then there are other methods, hydrotreating and hydrocracking, which are going to be covered in, I think, later topics, and FCC, fluid catalytic cracking. Again, we're not going to cover it here. But these are also fairly standard units that you would find in a refinery. Not every refinery has every combination of units, but for a variety of reasons, most of them have one or other of these. Now, to try to categorize these different processes, vacuum distillation and propane deasphalting are basically separation processes. You're not actually reacting anything. You're simply doing physical separations, whether it's a distillation, solvent extraction, something of that form. Once you get into visbreaking and coking, these are what they call carbon rejection processes. So what you're trying to do is to basically take the carbon out either by making coke or by making a heavy stream that takes some of the carbon and leaves you with some lighter material that you can use. And then again, just to hydrotreating and FCC. Hydrotreating obviously needs hydrogen, and the FCC, that's a catalytic conversion process. And it's been around for a long time, but it was developed, basically FCC was developed for aviation gasoline during the Second World War because they needed a really good way to crack materials like resid in order to make aviation gasoline for planes and other things for the war effort. So this was these were actually developed as like a crash government program. So, all right, the first thing we're going to talk about is vacuum distillation. Now, a vacuum column, we have to think about why we go to a vacuum unit. Now, vacuum units are tricky and they're difficult to operate in a certain sense because as soon as you go below atmospheric pressure, you run the risk that air is going to leak in to your unit. And because we're dealing with hydrocarbons, if you allow air to leak in, you always run the risk that you're going to have a hydrocarbon-air mixture, and if you end up with sparks and things like that, that you can have some kind of fire explosion. So typically vacuum processes are uncommon, but we need to use vacuum for a particular reason. The problem is with an atmospheric tower, there's a temperature limit. Once you get above a certain temperature limit, the crude oil starts to crack. You get thermal cracking, and you're going to end up with coke in the crude column and in the crude furnace. So you generally limit the temperature in the crude column and in the crude heater, and you're trying to avoid coking. So basically, you have a temperature limit. So in order to stay within that temperature limit, the other thing you can adjust is the operating pressure. And this is what we do with a vacuum column. Because as you know, as you lower the operating pressure, the boiling temperature decreases. All right? So obviously if you go up to a high elevation, like somewhere like Mexico City or one of the other high elevation places, if you boil water, it doesn't boil at 212 degrees Fahrenheit or 100 degrees C. It boils a little bit less because you're at a lower pressure. So the same principle applies in vacuum distillation. You're lowering the pressure so you can boil the material at a lower temperature, below the temperature at which it's going to crack. So that's the whole sort of purpose of a vacuum. There's a lot of complicated stuff there, but the main purpose is lowering the pressure so that you can avoid thermal cracking of the material. The basic operating pressure, 25 to 40 millimeters of mercury, and that's a pretty low vacuum. And they use steam in the furnace to minimize coke formation to make sure that the material goes through well. But then you have the question of how do you actually get to this level of vacuum? Because you need some way to remove material to get to this particular pressure. What they actually do is to use steam ejectors on the top of the column. This is a typical vacuum arrangement. The slide is not really that good, but here we've got atmospheric resid. This is a charge heater. We're heating it up. This is the vacuum column, and these are the various products. But you see right at the top there, we have some steam coming in, and these are steam ejectors, and they're basically taking material out of the column to maintain the vacuum that's on the system. Now, you also see that the W is for water, so we have some cooling water up there to condense the steam as it comes back through these ejectors. And this shows a little bit better. It's not the greatest slide, but you see up the top there, high pressure steam going through these ejectors, and then some water, that sort of thing. Now, because vacuum columns and distillation columns tend to be quite high, you can get into peculiar problems. And a number of years ago, I was called in on a unit that I didn't design, but it was built outside the United States, and I was asked to sit in on a conference call because they're having problems. They built the unit, they were trying to start up the unit, and they were having operational problems. And the problems were right in this area where the vacuum ejectors are, not actually in the ejectors themselves, but in these cooling water exchangers. And I'd never seen the plant, and I wasn't involved in the design, but we had a conference call and we talked through the problem, and they explained what was happening. When they tried to operate the unit, these exchangers at the top, they started to vibrate very violently, and they were up on a structure, and the things were shaking so much that they would shut the unit down. And in talking with them, I asked them some questions on the system, and one of the questions was on the cooling water system. And it turned out they had designed a once-through cooling water system. Now, a once-through cooling water system means they had a river, they would draw in water, purify it, send it through a system like this, and then it would come down and get discharged back into the river. And then I asked them some questions on, well, how high up is this stuff? And they gave us all the dimensions. And afterwards we did a few quick calcs. But basically, if you remember the old mercury barometer, let's say we have something like this. You have like a mercury level. If you fill this thing with mercury, then you end up with your 760 millimeters of mercury for atmospheric pressure. But up here, you basically have a vacuum, or basically the vapor pressure of mercury. So 760 millimeters of mercury, if you translate it to water, it's roughly sort of 30 feet or so of water. So you can sort of see what the problem was here, that they had a system where they were bringing in water from the river, and then they bring it up to a high elevation, greater than 30 feet, and then you have a pipe coming down that's open to the atmosphere. So you have a pipe that's open to the atmosphere, just like this, and you have more than 30 feet here. So up here in the exchanges, they were pulling a vacuum. So when they tried to operate this unit, this was the problem. They were having a vacuum in those exchanges, which are right up there. And the solution to the problem is that you have to put a restriction on the end of the pipe, so that instead of just discharging the fluid straight back into the river, you put an orifice plate or a valve or something on this to create some kind of delta P, so that then you'll keep this pressure above the vacuum condition. But again, it's a very strange sort of problem, and when we first explained this to them, they thought we were crazy, but they tried it and it worked. And it's just simple hydrostatics. But sometimes when you're building a unit and they started the unit up, and you have all of this other junk around here, you can't really see that there's actually a flaw in the system when it was designed. So anyway, the small things like that. But once you get the units running, they are a little So it's difficult to maintain the vacuum sometimes on these units, but obviously you need to do that. Now the next process we're going to talk a little bit about is deasphalting. So we take the resid and we use what is basically a solvent extraction process. The solvent is either propane, or it can be a mixture of other similar materials, ethane, propane, butane. You need something in the right boiling range and the right extractive properties. But basically what you're trying to do is to take out the material that you want. And the material that's left is the asphaltenes. They don't dissolve in the solvent. And so you're left with material that you can make asphalt for roads and things like that. And the process is used, and obviously we do need asphalt. We have lots of roads here in California, but we don't really need that much asphalt. Even though we build a lot of roads here, it's a useful product, but there's a limit to how much you can sell. But basically, it's a solvent extraction type of process. And this is a typical propane deasphalter. You can see the propane is coming in here as a solvent. And then we have what's called an extraction tower. And this is like a countercurrent type of tower. So the propane is basically going this way, and then we have the resid feed coming in and flowing back down this way, so they counterflow. And it's basically an extraction process. There is a little bit of distillation in here too. And then once you've done the contacting, then you go through basically some purification here to get the asphalt. And on the other side, you want to recover the solvent. Obviously, you need to recover the propane, and then you bring it back and reuse it. So it's simple in essence. Obviously, there's lots of pieces of equipment here. But basically, you have a solvent, you dissolve out the stuff that you want, and you leave behind this heavy asphaltene type material that you can make asphalt for roads out of. And then the other material, the deasphalted oil, you can use it as feed to other units, and it has some more value than the asphalt. Now these processes, there is in the iDrive, there is a very nice book on refining processes, and most of the things, whether it's an FCC, propane deasphalting, delayed coking, there are licenses to license these processes. And this one, for example, it's a licensed process, and you can see the little flow sheet here, and there's a little bit of a explanation about how the process works and typical operating conditions, feed types, and then some of the products, some stuff on the economics. This is sort of useful background if you want more information. But basically, it's a simple solvent extraction process, and you recover the solvent and reuse it. All right. So let's go. I don't know what your rules are on breaks, but is this a good time for a break? Okay, well,